So how we have defined carrier concentration, students? Yes. Students are able to hear me?
Yes, ma'am, audible.
Audible?
Yes, ma'am.
Okay. How we have defined carrier concentration? Fast. I want answers. Today we
Number of charge carriers
number of charge. Yes. Number of charge carriers per unit volume, right? So here we said that in intrinsic semiconductors, number of electrons and holes are same. So that's why what we have done first, we try to calculate electron concentration. So what is the expression we got for electron concentration? So where these electrons are present? Electrons are present in conduction band or valence band?
Valence band.
Free electrons, where they are present?
Conduction band.
Only electrons in conduction band, they will act as charge carriers. Electrons which are present in valence band, they won't take part in conduction because they are electrons without any energy. So what is the expression we got for this electron concentration, ma? Yes, I told you to remember that expression, right? It should be at the tip of your tongue. So what is that expression? What is the notation? What is the notation for electron concentration? We got it as N is equal to 2 into, yes, 2 pi m E star kt by h square whole to the power of what?
3 by 2.
3 by 2.
3 by 2 whole to the power of 3 by 2. Just 1 second, ma. Whole to the power of 3 by 2 into exponential of what we got? Exponential of EF minus
EC.
yes, EF minus EC by
KT.
Yes. So what is EF? EF, it is called Fermi energy level. EC is bottommost energy level of conduction band. Okay. So after this, what we were doing? I think we are trying to find similarly whole concentration in valence band. Right, students?
Yes, ma'am.
I think we simplified equation for density of energy states as well as Fermi-Dirac distribution function, right? So what is that expression we have taken for whole concentration? We have selected small energy interval and we said that let that number of holes in that small energy interval in valence band. What is that expression we got? Z of E D into what, students? I think we wrote it as 1 minus F of E.
F of E.
Okay, 1 minus F of
Yep.
E. And what is Z of ED? This we have taken it as first expression, right? What is Z of ED? Z of ED is density of energy states. And what is the expression we have taken for density of energy states? I hope you all are able to follow. Yesterday we have done this.
Yes.
Done this or not, students?
Yes.
So it is given as 4 pi by h cube into what?
2m
2mh.
E.
What is mh star? Mh star is effective mass of hole. Okay, so e to the whole to the power of 3 by 2 into, is it correct, students?
Yes,
What
ma'am.
I'm writing is correct or not?
Yes, correct.
So 2mh star whole to the power of 3 by 2, and here we should have e to the power of half, but that e to the power of half, we have replaced it as EV minus E whole to the power of half. Can you tell me why we have done this? Why we made that change?
Top of E will be 2.
Because when we go back to our energy band diagram,
Change in energy level.
so, yes, see here, we know that there are two allowed energy bands. Topmost energy band, it is called conduction band, and bottommost energy band, it is called valence band, right? And we are calculating holes, and holes are present in different energy levels of valence band. And what is our EV? EV is topmost energy level of valence band. And where we are taking that small energy interval D, what is the small energy interval D? It is the set of energy levels that are present below EV, not above EV, because what we have energy levels above EV, those are forbidden energy gap, right? So we are, because calculating hole concentration, so we have to consider energy levels which are present below EV. So that's why in place of E, what we are doing, we are substituting EV minus E. I think I have discussed this yesterday, right? I hope you people have no doubts about it. Yes, ma'am. Anyone has doubts?
No, ma'am.
Okay, then. After that, what is this 1 minus f of E? I have discussed about this. F of E is Fermi-Dirac distribution function, which gives probability of an electron occupying an energy level. Okay. Is it probability of an electron occupying an energy level? F of E.
Yes, ma'am. Yes, ma'am.
But what is 1 minus f of E? What is 1 minus f of E?
Probability of an electron not
Probability of an electron
Probability of
energy
an
level.
not
Elec-
occupying.
Electron not occupying an energy level.
Yeah, so probability of an electron not occupying an energy level, that is nothing but electron leaving an energy level. So that is nothing but formation of hole. And we got expression for f of E. What is that expression? I think simplified expression, we got it as exponential EF minus E by KT, right? So obviously, what will be 1 minus this? So this is nothing but, so this is equal to exponential EF minus E by KT whole to the power of minus 1. Right? So this whole to the power of minus 1. So whole to the power of minus 1 is nothing but, what will happen now? We know that e to the power of minus a is, suppose if I take e to the power of minus a, sorry, e to the power of a whole to the power of minus 1. How we can write it? We can write it as, so whole to the power of minus 1, we can write it as e to the power of minus a. So same thing I'm doing here. So if we simplify it, what we'll get here, students? We'll get it as exponential of e minus EF by KT. So this is what we are going to get for 1 minus f of E. Okay. And this we have taken as second equation. This is our second equation. And this is our third equation. So this is our third equation. So what we have to do next, we are going to substitute equations 2 and 3 in equation 1. After that, I told you people to do it. Yes or no? Shall I remove this? Yes, students, are you copying in your notes? Are you copying everything in your notes? Have you done it? So shall I erase
Yes,
this?
ma'am. Over, ma'am.
Yes, ma'am. Yes, ma'am.
Then what we are going to do now, next we are going to substitute equations 2 and 3 in equation 1. See, my handwriting is little bit odd because I'm doing it in digital slate. Don't panic. I hope you are able to understand my writing. Yes, students? We are able to understand or not? So what we are doing, we are substituting equations 2 and 3. So substituting equations 2 and 3 in which equation, students? In equation 1. Okay. So what we'll get once we substitute? So what is dP? dP is, what is dP? What does it represent? dP is? Yes, Yashwant, what is dP?
Z of E.
Number of holes.
Number of holes in energy interval D in valence band, right? Yes or not? Number of holes per unit volume present in energy interval D, and it is made up of two terms. One is the density of energy states, and another one is probability of existence of hole. So what is the expression we got for density of energy state? We got it as, so we got it as 4 pi by h cube So it is 4 pi by h cube into 2. Sorry, no. See, you don't have to wait for me. You start doing it in your notes. So 2 mh star. What is 2 mh star? 2 mh star is effective mass of hole. So this whole to the power of 3 by 2. Okay. After that, what we have? EV minus E whole to the power of half into what is 1 minus f of E? 1 minus f of E is exponential of E minus EF by kT d. Okay. Now what we should do next? What we should do next? What we have done in electron concentration. See your books. We are going to follow same procedure as we have done for electron concentration. So next step is finding
Density.
whole concentration in entire valence band. So now next step is we have of course got formula for whole concentration in small energy interval d. But now we need to find whole concentration in entire valence band. Okay. So VB is our valence band. So for that, what I have to do? I have to integrate Vp. So, and this whole concentration in entire valence band, it is given by P. And what are the limits of integration? Can anyone tell me what can be the limits of integration? Again, if I draw this energy band diagram.
EV2 minus infinity.
Yes, good. So here, for conduction band, what we have done? What are the limits we have taken? We have taken EC. EC is bottommost energy level of conduction band, and topmost energy level we have taken as infinity. Whereas for valence band, topmost energy level is EV, and bottommost we'll take it as minus infinity. Okay, so what are the limits of integration? Lower limit is minus infinity, upper limit is EV, right, ma'am? And of course, we have to integrate dP. So anyone has done this integration? Anyone has done this integration? No one has done it,
Equal to
right?
NV of exponential minus of E2 minus EV by kT.
You got that answer, ma?
Yes, ma'am.
Yeah, good, very good. So here, I'm just trying to put that dP equation here. So minus infinity EV so here we have EV minus E whole to the power of half, right, ma'am? Then exponential E minus EF by K3. Then next what we have to do? D. Okay. So we have to solve this integral. So solving integral, what we have to do, just we are going to follow same procedure as we have done for electron concentration. So how to solve it, students? How to solve this integral? So for that, we have to assume that let EV minus E is equal to X. Okay, so from this, what is minus T? Why minus T? Because here we have minus E and EV is constant. I already told you EV and EC, they represent energy values for one particular energy level. So that's why we treat them to be constant. And when I differentiate on both sides, this constant will become 0. What is variable? E is variable. So here we are left with minus dE on left hand side. So what we'll have on right hand side? Dx. Okay. And from this, Will try to get limits of integration. So what is our lower limit? If I substitute lower limit minus infinity, what is the value of x? What is the value of x? All are paying attention, students? Or only I am the one doing it? So what I have done here, as you can see, in place of e, if I substitute minus infinity, then it will become plus infinity. EV plus infinity will give us infinity. So what is the value of x? X will become infinity. Similarly, if I take upper limit value, what is our upper limit value? If I substitute e to be EV, then what will get? In place of e, if I substitute EV minus EV, it will become 0. So what will be our upper limit? Upper limit will become 0. And then here, what happens to if I take this expression? So if we take this expression, I think from this, what is our e? E will become EV minus x. So I have to substitute all this here in this integral value. Okay. So after substitution, what we'll get? So I'm going to make all this substitution. I hope you people are able to understand, students. Any doubts? Any doubts, students?
No, ma'am.
Okay. I hope you are able to see everything clearly and my voice is also audible to all. So what are the
Yes,
limits
ma'am.
now? Now limits
Yes, ma'am.
got changed from infinity to 0. Then in place of EV minus E, I have to substitute x whole to the power of half into, right, exponential of, what is our E now? E, we got it as EV minus x. So that I'm going to substitute here. So this is EV minus x minus EF, okay ma'am, by KT. Okay, so in place of d, what we got? Minus dx. Why minus dx? Because here you have seen d is minus of dx. Right, ma'am? So now how to simplify it? You have copied, students. All of you copy this in your notes. I hope all are maintaining notes. See, derivations will be clear to you only if you do it along with me. Okay?
Yes, ma'am.
So now how to solve this? Next, what we have to do, take out constant terms. What we have here, it is EV minus x minus EF, right? So this, is it minus EF? Yes. So here in place of E, we have substituted EV minus x minus EF. I think I can remove EV minus EF outside because EV minus EF, it's constant. So we'll take it outside. That is what I'm going to do now. Shall I clear everything, students? Okay. Now see here, I'm writing above. So P will become, I'm trying to take out all constant terms outside. So this will be 4 pi by h cube into 2. This will become 2 mh star, 2 mh star whole to the power of 3 by 2. Okay, ma'am. And what else I can take outside? Here we'll take it as EF, sorry, EV. See, you people, if you have any doubt, please ask me. Don't just keep quiet. You should come out with your doubts now. So EV minus EF by KT. And now what value is there for integration? So here we are left with this integral. So from infinity to 0, x to the power of half exponential. So once here I have taken EV minus EF outside, so I'm left with minus x by kt. Okay, and here I have, I think, minus dx. Okay, now what we have to do next, students? One thing, students, I hope you people know this. Minus of b to a. Suppose if I have integral with minus like this, I think I can write it as a to b. So if there is minus, I can change my lower limit to upper limit and upper limit to lower limit. You know about this, right? So same logic I'm going to apply here. So because here I got minus, I want to remove this minus. Then what I'm doing, I'm changing this limits value. So this 0 will come down and infinity will go up. So finally, what we are getting, so P is equal to 4 pi by h cube 2 mh star whole to the power of 3 by 2 exponential EV minus EF by KT So now limits will get changed from 0 to infinity. Okay, ma. So limits, they are changed from 0 to infinity, x to the power of half exponential minus x by kt dx. So there is no minus now. Why there is no minus? Because I have changed limits. Now, if you look at this integral, it is in which form? Is it not in the same form as the gamma integral? Yes, students? I think we have discussed about gamma integral. What is the value of this integral? My students, are you there? You are listening, students?
Yes, ma'am.
Yes, ma'am.
So what is the value of this integral? This integral, it is called as gamma integral. What is the value of this gamma integral? I think we have taken it when we are doing electron concentration. What is the value of this integral? See your notes. What is the value? I told you that it's a standard integral. So its value is kt whole to the power of
3 by 2.
3 by 2
Yes.
into pi by 2 whole power.
5 by 2 to
Yes.
the power of
So
1 by 2.
KT whole to the power of 3 by 2 into 5 to the power of half by 2. Okay. So this value we are going to substitute here. Once we substitute, can you tell me what is the final expression we are going to get? So if I substitute that integral value here, so we end up having it as P is equal to 4 pi by h cube into 2 mh star whole to the power of 3 by 2 exponential E minus EV minus EF by KT. In place of this, what we have to substitute? KT whole to the power of 3 by 2. So whole to the power of 3 by 2 into pi to the power of half. So pi to the power of half by 2. So now what we are going to do, we are going to put this equation in simplified way. So if you keep it in the simplified way, so we end up having it as 2 into 2 pi mh star KT by h square whole to the power of 3 by 2 exponential EV minus EF by KT. So exponential EV So this is our final expression for whole concentration in value.
My voice is stuck.
Second step is calculating whole concentration. Now third step is calculating intrinsic carrier concentration. Okay. So this is our third step. I hope you people are able to follow me. Right now. So for this, what we'll do, we'll use this logic. We know that in intrinsic semiconductors, all start copying in your books. So what we have in intrinsic semiconductors, N is equal to P. What do you mean by N is equal to P, students? What do you mean by N is equal to P? What is N?
Electron carrier concentration equal to hole carrier.
Yes, electron, number of electrons per unit volume in conduction band. What is P? P is?
Number of holes in.
Yes, number of holes per unit volume in valence band. And we know that only in intrinsic semiconductor, number of electrons and number of holes are equal in
Equal.
number. So that's why we are taking N is equal to P.
P.
Right? So therefore, what I'll do, as I told you before also, only in intrinsic semiconductor, number of electrons and holes will be equal in number. So that's why we'll try to get the expression for intrinsic carrier concentration, both in terms of electrons and hole concentration. So therefore, what I'll do now I'll consider intrinsic carrier concentration as if we take this intrinsic carrier concentration and I'm denoting it by Ni. So Ni stands for intrinsic carrier concentration. So this Ni, intrinsic carrier concentration, is nothing but number of electrons in conduction band, which is equal to number of holes in valence band. So that's why next what I'll do, I'll take Ni square. And how will I get this Ni square? Just multiplying expression for number of electrons and number of holes. So finally, I'll try to get expression for Ni as square root of N into P whole to the power of half. This is the logic we are going to follow in order to get intrinsic carrier concentration. Okay, students. So now what I want you people to do is, first you find Ni square. All of you start doing it in your books. So what is Ni square? Ni square is product of electron concentration in conduction band into hole concentration in valence band. What is the expression we got for electron concentration? I told you to remember those equations. They should be at the tip of your tongue. I think it's not difficult for us to remember those equations. What is N? Expression is 2 into 2 me star kt by h square whole to the power of 3 by 2 into what we have? Exponential
EF minus
yes,
CC by
EF
K.
minus, yes. So exponential EF minus EC by KT. Emma. And what about P? What expression we got for P? Just now I think we got expression. What is that expression? 2 into
2 pi by
yes,
2 pi by
2
h
pi
cube into mh square.
mh star KT by
H
h
square
square
whole power 3 by
whole to
2.
the power of, yes, whole to the power of 3 by 2.
Exponential EV minus EF.
Yes, yes, exponential EV minus EF by
EF by
KT.
KT.
Yes, so EF by KT. Okay, now multiply this. Multiply both equations. So if you multiply, what we'll get? So here we have, now here I have 2. Here also I have 2. So 2 into 2, it will become 4. Emma. And then next, take out common terms. See here I have 2 pi kt by h square. Here also 2 pi kt by h square. So this is whole to the power of 3 by 2, whole to the power of 3 by 2. I think you people know this. A to the power of m into a to the power of n. I can write it as a to the power of m plus n. Am I correct, students? Yes.
Yes,
Same
ma'am.
logic I'm going to apply here. So if we apply that logic, so we end up having it as 2 pi kt by h square whole to the power of 3 by 2 plus 3 by 2, how much? Cube. 3 by 2 plus 3 by 2 will be 6 by 2. So it will become cube. And then me star mh star whole to the power of 3 by 2. So because here we are left with me star and mh star, and both are whole to the power of 3 by 2 into, what about this term, this exponential term and this exponential term? I think you people know this, e to the power of a into, sorry. So e to the power of a into e to the power of b. What is this value, students? E to the power of a into e to the power of b is e to the power of a plus b. So here also I have two exponential terms. So we have to add. So if we add, what we'll get? So exponential of, so EF minus EC, okay, plus EV minus EF, and they have common denominator KT. Okay, so here there is a scope for cancelling EF and minus EF. So here we have EF and this minus EF will get cancelled. So we are left with EV minus EC by KT. Okay, students. So I'm going to write this again. Just we'll finish this and then we'll stop our class. So what is our Ni square now? Our Ni square is square of intrinsic carrier concentration. So here 4 into 2 pi KT
by h square.
2 pi KT by h square whole to the power of cube. Okay, whole to the power of cube into
ME star, MH star,
and then mh star whole to the power of
3 by 2.
2. Yes. And what about the exponential term? So because the TF has got cancelled, I think we are left only with EV minus EC by KT. Right, students?
Yes, ma'am.
Okay. But we need to get expression for only Ni. We got expression.
Inform them to call me, both the CRs of your class. Okay?
Okay, ma'am.
Okay, ma'am.
Okay. Okay, I'm ending the session. Go for lunch.
Bye, ma'am.
Bye.